Okay, guys, good morning. Happy Friday. Test will be returned on Monday. I've got a new handout, Chemistry of Dienes. I know you've been dying to get this handout. I'll send you another one today by email for printing for next week. Likely mass spec. Dienes, we looked at resonance, starting with dienes there. Yellow sheet, golden sheet. In the back, I always put golden rules of resonance. Back sheet, free information if you want it. If not, tear it off, throw it away. Free information. I'm recommending you look at it. Okay, resonance, conjugated dienes, non-conjugated dienes, accumulated dienes, benzene. Resonance, lots of theory. It's a little bit difficult starting with that. We did resonance down here. I don't think we named these guys down here. These are two very common cations. Now we can have substituents on the ring, or we can have more here. But alkene with cation next door is called an allylic. Allylic. Pretty sure it's two L's and then one L. Allylic. Cation. Cation. This guy's called a benzylic. Cation. Next to the alkene. Very common benzylic cations. Benzylic carbo-cations. We do resonance structures. Benzene ring, the first carbon next door. Cation. Conjugated cation. Very stabilized because the charge is delocalized by resonance. When we see this structure, the plus charge is not just there. We know the plus charge is also there, and there, because we are able to draw resonance structures, and that tells us. Okay? Whenever we see a compound that has resonance, one structure is no longer entirely valid. It's no longer really a good structure. True structure is a hybrid. But the true structure has these partial bonds, and that's cumbersome to draw. So instead we draw these individual really fake structures, but they look like real typical structures. And we have to understand that the true structure is a blend of these. We also have to understand the conjugation here. Okay? We have 3 carbons here, right? We have P orbitals. 1 electron, 1 electron. There's the pi bond we see, right? But over here, this is also a P orbital. It's empty. Or is it? It's empty right here, but it's not empty in real life. Because these are overlapping. And once they start overlapping, it's no longer just electrons, pi electrons here. The pi electrons are now all through here. Because once you have an overlapping system, it becomes one system. And the water spreads out all in there. I have an analogy of a garden hose. If I brought in a hose and filled it up with water, the water would go all throughout the hose. Why would it stay on one end? Why would it not flow through the entire hose? The electrons are all in there. And really what you have here is 2 pi electrons spread over 3 p orbitals. We're missing an electron. That's why it's a positive charge. We drew resonance structures last time. A lot of times you show this like this. It is, those 2 electrons are spread in there. But they're not equally here, so you can't draw a full pi bond here. But you also don't draw a full pi bond here. And charges, partial plus, partial plus. We drew this last time? That's the hybrid there of the 2 resonance structures. Okay, hopefully reviewed. The bond order. Which carbon-carbon bond is longer? 1 and 2 or 2 and 3? Actually the same. And we can see that from like X-ray crystallography. It's the same. The bond order, which equates to the bond lengths, etc., is 1.5 here and here. This is a perfect hybrid. This has limitations. That's theory. Now, functional working, you got to be able to go between resonance structures. We could just windshield wiper over, and that gives that resonance structure, resonance error between, okay? Again, these are both resonance structures. They're equal in energy, so you do not say one's major and one's minor, like we'll do later. But neither one's real. The true is in between. It's in between. But these are just nicer structures to draw. And that's how we deal with resonance. On the other hand, if you just have this cation here, that's it. There's no resonance you can draw there. Basically, that compound has no pi electrons. I mean, there's no alternative structure for that cation. You're not moving that charge anywhere. This charge is not delocalized. There's no resonance at all. Resonance involves pi electrons. Okay, benzylic. We drew benzylic. I think that's where we left off at. I can't quite remember. It was Monday. Over here. Oh yeah, we did a little bit of this. Stabilization of a cation by lone pair. We did that, yeah? Yeah, we talked about that. The major resonance structure is actually the one with charge on oxygen. Because they have more bonds. Did we do resonance structure down here?
No.
I don't think we did. The theory of understanding the pi orbital overlap, one thing, but then being able to draw resonance structures, moving electrons, that's sort of another thing. Do we have a pi system here, an extended pi system of conjugated p orbitals? It can be 2, it can be 4, or maybe it's 10. How many p orbitals are conjugated here? This molecule. How many p orbitals are conjugated? They're lined up. You got to see that. It's 4, right? 4. Boom, boom, boom. Right? There's 2 here, right? You see the pi bond, right? That's 1, 1. That's pi bond, right? We covered pi bond week 1. Week 2. Pi bond. Pi bond. Okay? Here, what's the hybridization of a carbo-cation? There's 1 H there, so what's the hybridization? sp2. If you graph it, you'll see you have an empty p orbital. Empty p orbital. Okay, what's the hybridization of this nitrogen? It's got 1 lone pair, which is hybridization. sp2, right? And the lone pair is in a p orbital, right? Didn't we do this? Anytime a lone pair is next to a p orbital, we want to put the lone pair in a p orbital. Why did we do that? So we can understand resonance. It's there. And so you got 4 conjugated. You got 4 p orbitals. How many electrons in the pi system? Turns out that it's 4 here, even though it's a positive charge. That's because we're going to be able to draw, well, it is 4. Basically, once it becomes 4, then here comes your theory. Those 4 are spread out all through here. Okay? It's like a garden hose. They really are in real life. Okay? This becomes cumbersome. We could draw that. Let's go over and do resonance structures, though. How do you stabilize a cation? Move electrons towards it, right? Okay? We could do this. We could swing these over, windshield wiper. That means we're putting a pi bond over there between carbon 2 and 3. That gives boom, boom, boom. Boom. Positive there, right? That's what the arrow means. I'm going to call this the A arrow. I'm going that way because the next one is not going to come from here. We can also do another resonance structure here, right? Are there any other source of electrons we can move towards the cation? Yes, a lone pair, right? Let's move that in. Let's call this the B arrow. And what does that give? Little bond over there. Charge on nitrogen now positive. Right? Two different resonance structures we can draw. In both cases, we have delocalized the charge. We've moved the charge to the other carbon, and we've moved the charge to nitrogen. All three of these are cations. Major, minor. Which cation do you like best? Which is the best? As if you had to choose among the three, which one do you like best? Bottom right? Yes. This is major. Why? Just like we said up there, and you will see it again. More bonds. So you might ask, why didn't we just originally draw it like that? Well, you can draw any original, and then you can draw them all, and then you can say which is best. But if you had to say, well, what's the true structure here? Kind of this. They're all spread out in there. We got double bond character between the end carbons, the middle carbons, and also between carbon and nitrogen. We see that double bond character through looking at the individual fake structures. The charge is spread out. We have some charge here, some charge on that carbon, and some charge on nitrogen. Okay, the hybrid is just a blend. Okay, what do we have between carbons 1 and 2? Double, but some single. So it's not double all the way, it's a little bit less than double because we have some single bond character. Now we're never going to get anywhere like 1.8, 1.7. If it's between single and double, we're going to call it 1.5. How about between carbons 2 and 3? Single, but some double bond character. So it's not all single, it's a little bit more than single because of this double bond contribution. So it's a bond and a half. And the same thing over here. Because it's single, but some double bond, which gives it more than single. Now this is not a perfect blend. But usually when we do hybrids, we just try to make it all the same. Because it's even more cumbersome to talk about. There's more electron density where, well, we can assess that. There's more electron density between which two atoms? 1 and 2, 2 and 3, or 3 and nitrogen? Right here. How do we know that? Because we said that this was major. Since this is major, the hybrid looks more like this. That's what we're saying. It's like the kid looks more like mom. The hybrid looks more like this. That's what that means. Thus, there's a good amount of double bond character here, and in the hybrid, actually between here and here, there's a more, it's the most single bond character of all. So instead of 1.5, maybe it's like 1.2. But here's your hybrid. Don't forget the H's. Charge, partial plus here, partial plus. And the original was here, and partial plus here. Note that none of the positive never falls on that carbon, does it? We look at our fake structures to assess the hybrid. We have delocalized the carbo-cation by resonance. Because if you can spread this charge out, it's almost like maybe a third charge here, third charge here, and third charge here. That's better than having a full positive on a single atom. This is a resonance-stabilized carbo-cation. So there's theory, and then there's moving electrons. And, okay. Resonance can dictate outcomes of alkene reactions. Got an alkene, HBr, we'll be doing a hydrobromination. Which product are we going to get, left or right? Well, we know these reactions, the outcome is based on which carbo-cations are you going to form, right? We're going to form cation on top or bottom. That's the question that we've always asked. Would you rather form cation on top or bottom? Well, let's look at the two cations. I would probably do that, draw them, then let's focus on the two cations. Let's do one thing at a time so we don't get confused and all jumbled up. We can have cation here, new H here, we're attacking H, right? There. The other cation would be, attack H there and leave cation here. Which cation's best? Bottom one. Why? Because it's resonance stabilized. This charge is not all on carbon. Half of this charge, actually more than half of the charge, is on nitrogen. Because which of these is your major resonance structure? This one here, right? Same reason as above. More bonds. More of your charge, this is major, so it's the hybrid looks more like this. More of your positive is actually on nitrogen. This has no resonance. What resonance would you draw here? Very important. What resonance structure would you draw here? Question?
Why would the bromine not cause steric hindrance if we're not going to nitrogen right there next to it?
That's just not a relevant point. The reaction is based on where you're going to form carbo-cation. Right? That's how we've always predicted outcomes of alkene reactions. Question is, where are you going to make cation? The thermodynamic stability of the products is not applicable. The reaction is not driven by thermodynamics of product. The rate determining step of this reaction is forming the cation. Forming the product is not relevant at this point. Keep asking. What resonance would you do here? This cation is not being conjugated. Okay? If we drew the pi bond, or p orbitals, you can call this an empty p orbital. Is there a p orbital next door, though? I mean, there's two H's there. There's no p orbital here. There's no p orbital there. Is this lone pair in a p orbital? No, that's an sp3 nitrogen. Lone pairs in a hybrid. No reason for it to be in a p orbital. That's just one empty p orbital. Anytime we do resonance, you have conjugation. If you think about the theory, you have p orbitals overlapping. There is no overlap there. This is your better cation. Because this is a better cation, this is your product. You can always work with any resonance structure. Remember, neither one of them is real. To get there, what happens to Br minus can just attack there, and you get your product. However, you can always work with that resonance structure. Okay, you're out tomorrow night, you're like talking about resonance structure, someone says, no, you have to work with this resonance structure. You say, no, you can work with anyone. They're all fake. Why are you making me work with this fake one? Why can't I work with that fake one? Well, you can. You attack here and move these back over. And this arrow movement also gives that problem. Because when you move it back over, you get the lone pair back, right? By the way, if this is the major one, wouldn't you, if you had to choose, wouldn't you work with this one? In the future, we maybe won't, though. We maybe won't even draw the major resonance structure, but we'll know it's there, and we'll add here. Br minus is not going to attack here, then you would have 4 bonds of nitrogen, and you'd have a lone pair on carbon. This is the way it goes. The nitrogen gets neutral by getting these electrons back. Okay? How about below? Which product do you think would be formed? First off, alkene reactions, we don't react benzene. Okay? That's organic too. We have one alkene. What's going to be the regiochemistry? Iodine on the benzylic carbon or not? Where are you going to make cation at here? It'll be a benzylic cation. All right? H plus, right? Tacked like this. Benzylic cation. UH there. And last time we drew resonance structures of the benzylic cation. Very stabilized cation. This is the one that's going to form. And then the I minus attacks there and you get that product. Right? We put cation there. By the way, they're both secondary. But there's more to it. This is secondary with resonance. Resonance delocalized. It's just plain secondary. No resonance here. There's no P orbital on either side. There's no conjugation and thus no resonance. It's an isolated cation. Delocalized cation. Better. Regiochemistry. Stabilization of anions. Questions? How do you stabilize an anion? Move electrons towards it, or you got to move electrons away from this carbon? Away. Move electrons away. Okay. Resonance here. Let's do the resonance structures first, and let's look at a little bit of theory. We got to know the orbitals here. Move it away. That's your starting point. Especially if you have a lone pair that's conjugated. These electrons can move in here, and these can be moved out. I call this the old in and out. We got the windshield wiper, we got the in and out, right? What does the arrow movement give? You got to know what each arrow moves means. Why do you need to know that? Because use of arrows helps you tremendously to understand what's going on. That should then give what? We have double bond. Now here, right, moves in to make the second bond. We're not moving the lone pair over here. It's falling in to make pi bond, but these we're moving out. Instead of a bonding pair, we're going to move it out onto that carbon as a lone pair, non-bonding pair. That arrow movement gives that. Now this is minus over here. Make sure you check your charges and say, okay, do I understand why that's minus? Because if you always gloss over it, then when it comes time to do it, you're going to, oh, I never did that. It's minus because there's two H's there. And if you can do a charge, it's minus. There you go. Which one's major? They're the same. Equal energy. There is no major minor. Equal contributors. The child looks exactly like between mom and dad. Perfect match. That is, if we drew the hybrid's going to be easy to draw and consider because it's a perfect. How many what's the bond order between 1 and 2? Well, it's not double and it's not single. What's an average of double and single? 1.5. Over here, it's not single, it's not double. What's the average? It's a perfect average. Perfectly 1.5. The minus charge. Is there any minus charge on this carbon on the left end? Yeah, you see it? You see the minus charge there? Look over there to see it. Yeah, it's there. It's partial minus. And that's partial minus. And if you could see the real compound, it would look like that in terms of the electron density. Perfect amount on each side. These are actually fake structures, right? It's the same story. Here we go. Orbitals, though. This implies P orbitals. Well, if you look at any structure, you can get going. You can see pi bond on the left. Let's just draw the orbitals. One electron makes pi bond here. But what about over here? What's the hybridization of this carbon with the lone pair? Well, anytime a lone pair is next to a p orbital, the lone pair is going to want to be in a p orbital? Yes. That lone pair is in a p orbital. So we have 2 here, 1 and 1. But guess what? Once they start conjugating, it's real all together. And these 4 are spread out all in there. Okay? So we got 3 p orbitals with 4 pi electrons all spread in there like a garden hose. Pi bonding, resonance, conjugation. Understanding the resonant hybrid. And if you look at this, it's a perfect the 2 carbon-carbon bond lengths here are equal. Perfectly equal. Where maybe a year ago you would have said, well, double bond shorter, so it's shorter over here. But it's not isolated. It's not an isolated structure. It's a resonance, a localized structure. Okay? How about this guy? Can you draw resonance structures of this? If there was an H here, that would be called phenol. Okay? Phenol, right? pH. Phenol. You know that functional group? You can have substituted phenols. The anion of a phenol is called a what? A phenoxide. Phenyl oxide. Phenoxide. Okay? Can you do resonance of the phenoxide anion here? What do we want to focus in on? First off, we got a negative charge. Resonance is great with charges. I'd focus in on the charge. And that charge has lone pairs. How do you stabilize a negative? Electrons away from it. What electrons? The conjugated ones? Well, there's a lone pair and a p orbital here. That's what's conjugated. Yeah, the lone pair is a great place to start with resonance if a lone pair is conjugated. This lone pair, move it in. Well, you have to move something away here because we don't want to show a fake structure with 5 bonds. That sounds funny, right? Don't show fake structures with 5 bonds. Because the 5-bonded fake structure will really be bad. Right? So we got to move something out. Well, what do you want to move out? You want to break this sigma bond? No, you don't move sigma bonds with resonance. That's one of the rules of resonance. Back page. What are other rules of resonance? We've been doing them. Every resonance structure has the same net charge. What's the charge of this structure? Minus. What's the charge of this resonance structure? It better also be minus. Every resonance structure has the same charge. There's other rules of resonance that we've done, but I may have not called them rules of resonance. They're on your back page. You only move pi electrons. Never move a sigma bond or sigma electrons when you're doing resonance. It's a sigma bond. If you did that, you'd be breaking open the ring. No. We move the pi bond, okay? You can consider either one of these the pi bond. Move it here. In, out. What does that give? Well, let your arrows be your guide. We now have a double bond between the carbon and oxygen, 2 lone pairs left. We didn't do anything here and here. What's now on this carbon? A lone pair. All right? Every resonance structure has the same net charge. If this is minus, that better be minus. Where is the minus? It's now on the carbon. We have delocalized the charge. Can we draw other resonance structures? Yes, you can keep going. These electrons can move here, and we can move these out. We didn't do anything there or there. My rings don't always look connected. If I try to connect them, they'll look too odd sometimes. We now have pi bond here, and here we move the pi bond out to become lone pair, and now that's minus. We can keep going. These electrons can move here, the pi bond can move out. in and out. Resonance arrow. Nothing here. Boom. Pi bond there now. And we move the electrons out to there. Now that's a minus. We can keep going. These electrons can come here. What do we move out? Pi bond. Well, the pi bond moves out onto oxygen. And I'm just going to call this original. Although the pi bonds in the ring are going to be moved. Over here, the pi bond is on the left. When we get over there, there'll be no pi bond on the left. That's because you can do resonance in the ring without moving the anion. I'm not going to do that. Usually I will say, draw resonance structures that involve delocalization of the charge. We delocalize it to that carbon, to that carbon, to that carbon. If we do this, it goes back to the oxygen. Since it's back to the oxygen, it's not a different resonance structure for what we're doing here. And the hybrid is going to thus look like what? Well, if you look at it, you got partial bonds all the way around. Partial minus, partial minus, partial minus, partial minus. Importantly, this carbon, and this carbon are the ones that become partial minus. We see that from the resonance structures there, there, and there. Which one's major? The hybrid looks more like which one? This is a generic hybrid. We haven't said, maybe there's more electrons here versus here. Which one's major?
The original?
They all have the same number of bonds if you count them, because here we made a bond, but also we broke a pi bond. Same number of bonds. This is major. Two reasons. One of them is a clear reason. Answer, would you rather have minus on oxygen or carbon? Oxygen more electronegative. Okay? And, I'm just going to say minus on oxygen here. Okay? Same number of bonds. It's also kind of good that the benzene ring is sort of fully intact, although it sort of is there, but it's sort of. Nice benzene ring is usually a good thing, but that's an intro-level view of it. Negative on oxygen. That is, the hybrid looks a little bit more like this one than the other ones. More of the minuses on oxygen than these carbons. But the charge is delocalized onto these carbons. That helps stabilize this. All right? On the other hand, if we drew just this anion, no pi bonds in the ring, there would be no resonance there. You cannot draw another resonance structure. This anion is more stable because of resonance than this one. Make sense? Delocalizing the charge stabilizes the anion, the charge, the species, the compound. Which one's more basic? Which one's a stronger base? Which one is more dying to have to react with an H plus and go back to neutral? This one. It's less stable. I gotta have a proton. I gotta go back to neutral. This guy's like, I'm all right. I'm hanging out here. I don't really have a full minus. My buddies are kind of taking on some of the charge here. They're carbons, but they can take on a little charge. We're all hanging here together. We're cool. Yeah, protons are nice, but we're cool. I need a proton. I'm just a big minus. Boom, big minus. There's no resonance here. Make sure you understand why. Resonance delocalization. Neutral molecules. We started with a neutral, but it did not have any heteroatoms, the diene, and so it was kind of hard to draw resonance structures. When you have heteroatoms, easier because you have sort of more intuitive polarity. Aniline. It's isoelectronic to what we just looked at. It's benzene ring with atom with a lone pair. But the one we just looked at, though, this had a minus charge. Here it's neutral. But that ain't going to change a thing other than we got to keep track of charges. We draw resonance here. And back in August, we said that this lone pair was in what type of orbital? P orbital. Because anytime a lone pair is next to a P orbital, it's going to be in a P orbital. Yeah. Let's start with the theory real quick. I would not even draw this. P orbital. But you also got these other P orbitals, 6 of them. And these P orbitals are all interacting. How can we show that? Well, let's draw some fake structures to show that. Now, there's no charge here, so we can't say, okay, do we move electrons towards or away? So we don't have that sort of starting point. But what we do have is a lone pair that's conjugated. If you have a lone pair that's conjugated, that is a great place to start with your resonance structure drawing. Just like the previous example, these electrons can move into here and these out. That gives us this lone pair here, and we did nothing here and here, correct? But this structure has charge now. What's the charge of the nitrogen? Positive. What's the charge of the carbon? Just like in the previous one, negative, right? What's the net charge of this here? Neutral. Well, then the resonance structure better be net neutral. Is it net neutral? Yes, net neutral. There you go. You can keep going. Okay? I'm not going to keep going because it's just like the previous one. The difference is this is nitrogen instead of oxygen, and it's neutral instead of the oxygen anion. The alternative would be if we drew just NH2 here and no pi bonds. That amine has no resonance. I mean, there's no p orbital here. This lone pair is just sp3. Which lone pair, which nitrogen has more electron density? These are types of questions you have to be able to rationalize in a sense. Which nitrogen has more electron density? The nitrogen of aniline or the nitrogen of this cyclohexylamine? Which nitrogen has more electron density? This one, right? Why does this one have less? It looks like it's got a lone pair. We know the lone pair is really not on the nitrogen fully, is it? It's delocalized. Some of this electron density is over on this carbon. And that carbon, if you keep drawing resonance structure. And that carbon. Resonance delocalizes the lone pair. We don't call it charge here. But the electron density gets delocalized by resonance. There's no resonance here. This nitrogen has a more electron density than this. Which nitrogen is going to be more basic? The one with the more electron density, right? Yeah, aniline is less basic. Now, back in August, we said this. Anytime a lone pair is in a p orbital, typically the lone pair is not going to be basic. Did we say that? Well, that's why we said it, because if it's in a p orbital, it's busy doing resonance. It's conjugated, it's delocalized, so it's not going to be basic. Certainly as basic. There's no delocalization here. You cannot draw a resonance structure here. That lone pair is on that nitrogen. Okay, when you're dealing with benzene rings, you often have substituents on the ring. And certainly when you move forward to organic 2, you'll be doing lots of this, so we can start now. What if we put these substituents on here, like this ketone group? What type of resonance structures can we now draw, like into this group? Okay, that is, we can do it here, like on the phenoxide. But can you keep going and draw any more resonance structures? You know, you just keep going, you know, you just boom, boom, keep going. In, out, or whatever. In one of these, you will be able to draw resonance structures into the ketone or carbonyl. The other, you will not. But then you should be able to answer questions like there. The question is below the structures. Which amino group of the two compounds above is most electron rich? Please try these types of questions. We'll either talk about them or I may send out like a little key or something. Pi bonds to heteroatoms. Okay, up there, neutral. We're under neutral. We started with a lone pair. Lone pair was conjugated. Here we do not have any conjugated lone pairs. Oh, hold a minute. We do have two lone pairs. Are these lone pairs in a p orbital? No, if you graph this, you'll see that both of those lone pairs are in hybrids. They're not in p orbitals. We did that back in August. All you have here is you've got the pi bond. We'll draw it like this. Right? That's it. The two lone pairs are in the trigonal planar. I'd have to draw it like this. Okay? That's a trigonal planar oxygen. Hybrid, hybrid, hybrid. With one p orbital overlapping with this one p orbital here to make pi bond. Lone pairs are not. Thus, since a lone pair is not in a p orbital, you will never do resonance with these lone pairs. Lone pair has to be in a p orbital to do resonance. Resonance is p orbital stuff. So forget about it. Okay? Here we go. Can you do resonance with just one pi bond? Yes, you can just sort of, instead of the in and out, you can just sort of do the out. I can just move this polarizer. I can move it up. And that would give, we're moving this as a lone pair up. It does have 2. Now it has 3, and it's a minus, and this is plus. Now, that compared to this, it's a resonance structure because all we did is move pi electrons. What's the hybrid look like? First off, which is major or minor? This is major. Why? 4 bonds. And on day 1, if we were drawing Lewis structures, if we had had this, we would have said, hey, we need an octet here. And we would have moved these in and came this way. And that's major. This is minor. That doesn't mean it doesn't contribute a little bit. Does this make sense in terms of polarity, electronegativity? Would that oxygen like to pull that pi bond? We're pi bonded, but I'm an oxygen, so I'm greedy. How about if I pull? Right? It's greedy compared to the carbon. It pulls. Well, Which bond is held tighter, the sigma or the pi? Sigma's tighter. That means the pi bond is okay, we got a sigma strong and a pi. The oxygen can pull on that pi bond because it's not as strong of a bond, so it can pull on it. The pi bond is more polarizable. And this is where the oxygen solid just took that pi bond and said, I'm just taking the electrons. But hold on, does it take it completely or does it remain with like a pinky bond? I'm not going to take it completely, but let's just kind of pinky bond some. So we got a full bond and then maybe a pinky bond. But I'm holding on most of the electrons. How can we show that? Something like this. A full bond and a pinky bond. That is, if these are the resonance structures, what's the blend between a double and a single? Somewhere in between? Yeah. Bond and a half. Charge. What's the charge on the oxygen here? Partial minus, partial plus. Here we go. That's acetone. You use it to wash your glassware. If you could look at it, it would look like this. The electrons are more towards the oxygen. Like polarizable pi bond. But anytime we show acetone, we're going to show it like that over there. That's just simpler to draw. Okay? So this is resonance. The main thing here is we always polarize pi bonds this way towards the more electronegative atom. We would never do the opposite. And when I say never, I mean never. We would never polarize the pi bond this way. That would give an oxygen with just 2 lone pairs, and a carbon with a lone pair, that would be minus and this would be plus. This is bad. Don't do this. This oxygen will hunt you down and make you pay. Oxygen does not have an octet now. It only has 2, 4, 6. All right? Resonance? No. This goes against your polarity, your electronegativity. Very bad. It is a resonance structure, but it's very bad and we typically never show it. Okay? Up there, polarized towards there. Show resonance structure of this guy. Question?
For the lineage group, it has very bad. So it wouldn't be a contributor? Is that what you're basically saying? Like, you said it is a resonance structure technically, but it just wouldn't be a contributor to the major?
It's a resonance structure because all we did is move pi electrons.
But it wouldn't.
So that makes it a resonance structure. But how good is it? It's so bad that I say it's worse than 0. Remember that movie Less Than Zero? Yeah, 1988.
Right. So you,
Less than 0. Very bad. You can argue if it's a resonance. How much does it contribute? It contributes 0% to me. Okay? It's so bad I wouldn't draw it other than to warn you not to do it. Okay? Intuitively, we want to move the pi electrons towards the oxygen. Just like this. If I had a garden hose laying flat, the water would spread out. What if I raised one in? Would the water still spread out or would it flow more towards this left? Gravity, right? So if I raise this in, would more water go towards the left of the hose if there was room to move? Gravity makes the electrons go that way. The electronegativity makes electrons go that way. How about that for an analogy? Make sense? All right, that's what we got here. These are not equal contributors. Well, I'll talk about this. This is so bad we ain't even going to consider it. Resonance here. One thing you guys want to do often is say, okay, I'm going to move pi bond over there. Right? Haven't we done that before? And make this. Well, here's what you guys will do. Okay? Don't do this. There's two here. You guys will do this, and then you will draw 3 lone pairs here. And I'm like, where did the 3rd lone pair come from? Because there's 2 here, and all you did was move here. Ding, ding, ding. Okay. There is no lone. There's only 2. You started with 2. No octet. Bad. See, the difference is, if this was an alkene, you can do this. Because we can leave a carbon as a carbocation. That's what we did before. You can have a carbon as a no octet cation, but never leave an oxygen or anything else, nitrogen, with a no octet cation. Bad. So what resonance structure can we draw here? How can we delocalize this charge? Do we have any other electrons we can move towards this cation? Yes, right here. Move these here, and we get double bond to F. Positive charge there. That fluorine has a positive charge, but the major thing there is it has an octet. If it has an octet, it don't mind being positive. And that's your only resonance structure you can draw here. Which is major, which is minor? That's actually the major structure. More bonds. If you could see the real resonance hybrid, it would look more like the one on the right. More of the positive charge here is actually on fluorine. Question?
I thought fluorine doesn't like to share at all. Like, doesn't like to make multiple bonds.
Good question, but really the answer here, as long as it has an octet, it doesn't mind sharing. Because sharing gets us another bond. And even fluorine likes the bond. The question is, how much does it want to share? Does it share completely? No. We'll end here. It doesn't share completely. It's sharing some, though. Okay? Some of that electron is there to make the hybrid look like this. It's not a complete share. Fluorine doesn't want to completely share. I agree with Jim. Question? No, it isn't a P orbital. Yeah, one of these lone pairs is a P orbital. Anytime a lone pair is next to a P orbital, yeah. One of these lone pairs is in a P orbital. You gotta know that. Have a good day, guys. We'll be downstairs. Downstairs today.
No, nobody's there, so